that there are particular pins on port 3, pin 30, pin 31, which are the RxD and TXD for the serial interface, which is hardwired to a special register inside the 8051 known as SBUF. And associated with SBUF, which is actually two 8-bit registers, one for transmit and one for receive, there are two flags called TI and RI, transmit interrupt, receive interrupt, and those flags actually are present in another special function register called SCON. Okay, so there's SBUF, SCON. SCON, you're expecting to know what all the bits in SCON do. Pretty much all of them. There's things like the receiver enable. There's the 9th bit for transmit and receive if you're transmitting 9 bits of information, because SBUF is only an 8-bit register, 2 lots of 8 bits. And most importantly in SCON, there's actually 3 bits to determine the mode of operation for the serial interface. And one of those bits, SM2, you can ignore. We're not doing anything with it, just leave it 0. But SM0 and SM1 allow us to choose between the 4 main modes of operation on the serial interface. Okay? Mode 0, we might just about do today. It's a special shift register mode. Mode 1 and Mode 3 are 8 and 9-bit UART modes, Universal Asynchronous Receiver and Transmitter modes. Okay? And in both of those cases, the rate at which the bits are actually transmitted and received, or sampled if you like, is determined by timer 1. Mode 2 is a UART mode as well, but in that case, the clock that's used to transmit and receive the data does not involve timer 1. It's directly divided down by the crystal oscillator. So in summary, we had this slide here, which is actually showing you the 4 main modes and the pulses that determine when to transmit the individual bits and when the bits should be sampled, how that information is derived, those pulses, how are they derived? Are they coming from the on-chip oscillator or are they coming from timer overflows? If you were choosing to use timer 1, so you're using modes 1 and 3 for the serial interface, it is your job to configure the timer appropriately. Okay? It doesn't automatically happen. You have to manually program the timer to an appropriate mode. And you're aware of 2 timer modes that we use quite a lot. Timer mode 1 and timer mode 2. Timer mode 1 is the 16-bit mode. Timer mode 2 is the 8-bit auto reload. And you could use either of those with serial interface modes 1 and 3. So it's starting to get complicated. So you've got the serial interface, modes 1 and 3, use timer 1. But it's up to you to configure timer 1 appropriately to generate the overflow pulses. In passing, there is another register that we need to be aware of, which is this register called PCON. Primarily it's used, I think, for power control, but it has a bit in the PCON register called SMOD. Now why they put it there, I have no idea, ask Intel, but the SMOD bit in the PCON register affects how much we divide the timer overflows down by, or the other sources. So if I go back to here, you can see, depending on this SMOD bit, in mode 2, we've got a choice to divide by 64 or divide by 32. In modes 1 and 3 of the serial interface, we can divide by 32 and 16. The default is for SMOD to be 0. So normally you'd be dividing down by 32 here and dividing by 64 there. And if you're happy with that, you don't need to touch it. If you're unhappy with it, you would have to go into the PCON register and change it. Now you can't change the SMOD bit itself because it's not a bit addressable register. PCON is only byte addressable. So what you would have to do is to take the whole of PCON, load into the accumulator, change the bit you want to change, and then write the whole thing back. And we played around yesterday, with trying out to generate 9600 with a 12 megahertz crystal. And we tried two ways of doing it. The way that's shown here gave us a 7% error, which is probably too bad. It wouldn't work reliably. And then we thought, okay, well, what if we were to change the S mod bit, so we divide by 16 as opposed to divide by 32, and we actually ended up with a worse result. It was an 8.5% error. So, but there's a whole variety of the ones I mentioned in passing, that this particular strange crystal frequency is often used when you're going to make use of the serial interface, because this particular number, when you divide it down by powers of 2, tends to give you almost precisely all the right baud rates, all the standard baud rates, which is why you see these percentage errors here of almost 0. There's more examples on the notes anyway, so there's one here. I'm not going to work out the details, but basically we've been asked, and this is what we got up to yesterday, so write the instruction sequence to initialize the serial port to operate in 8-bit UART mode at this baud rate, 9600, and we're going to use timer 1 to provide this baud rate, and we've been told in this particular occasion this is the crystal that we're going to be using. Okay. So, well, actually I will do a bit further. Going back a bit, you would remember that we could try it, for example, the normal thing, divide by 32 here. So I haven't got my calculator with me today, so we'll only be approximating some things, but I'll just remind you how we would work it out. So effectively, what we're being asked to do is to use timer 1 to generate the overflows. So those overflow pulses are then going to be fed into a divide by 32. And then they're going to feed into SBUF. And we've been told that these pulses that basically control SBUF, we need 9,600 of them per second. So therefore, you can work out what the overflow rate you should have, because it's going to be 32 times 9,600, whatever that is. So 9600 times 32 will give you this thing here, which is probably, I'm guessing, 307 kilohertz. I have no idea what it is. It's in the slides. What we then have to do is to say, okay, well that says what frequency we need here, but what frequency the overflows happen is a function of two things. How much this has got to count up to reach the overflow, and also, remember, this is being fed by a crystal oscillator. So depending on what crystal you've chosen, that will influence the decision. Now we've been told we're using an 11.0592 megahertz crystal, which means that, if you like, the frequency at which this is going to do anything is 1/12 of that, because it takes 12 clock pulses to do one machine cycle. So 1/12 of that is probably about 900 and something megahertz. So, sorry, 0.9 something megahertz. I don't know. Let's just pretend it's 0.970 megahertz. I have no idea what the number is. Just divide that by 12. So that's the frequency at which pulses are causing this to count. If you like, this is the count frequency of the counter. But we want the overflow frequency to be this. So what you would do is divide this thing, and I have no idea what the number is, by this thing, which will give you how many steps you need in your count. Now when you work it out, it's on the slides, I think in this particular case it is exactly 3. Okay? Which means that when we reload this timer, we need to reset it to 3 steps away from 0, because it's going from FF or FFFF to 0 that causes the actual overflow. So if you imagine, let's assume we're using an 8-bit mode. An 8-bit mode, that's the 0. 1 less than that would be that. 2 less than that would be FE. 3 less than that would be FD. If you count 1, 2, 3 steps. If you can't work out what the number is, you can always do a reload of -3 in this case, and the assembler will actually work out what that is for you. Anyway, so if you like, when the timer goes from FD to FE, nothing happens. When the timer goes from FE to FF, nothing happens. When the timer goes from FF to 0, that's when we get the overflow pulse. And then it's up to how we configure the timer, what happens next. If we're using 8-bit auto reload, then whatever's in timer high 1 will automatically be reloaded into the low part of the timer that's doing the counting. If you're in a 16-bit mode for the timer, so it will have gone from, the last thing would have been FFFF through to this, you would need to do the reload yourself into the timer. And both of those options are open to you depending on how you've chosen to configure your timer. So that was the question we were posed, and we've kind of roughed out what we think the answer should be here. And in fact, the calculation's been done for you here. So this is the answer. So it's saying, they're choosing, whoever's prepared the slide, which was probably me a long time ago, I've chosen to use timer 1 in the 8-bit auto reload mode, which is actually timer mode 2. So I'm using the serial interface in mode 1, which is the 8-bit UART mode driven by timer 1. And the timer is configured in mode 2 in order to do it for 8-bit auto reload. So, in order to use the serial interface in this way, these are all the registers that you're going to have to fiddle with. The good news is you don't have to fiddle with them more than once. You just configure it when you first basically power up the microcontroller, and thereafter, unless you want to change the baud rate, just leave it as it is. Okay? So you can see here, this is what I'm doing to SCON. It's these 2 bits which matter here, and I don't know if this is the right way around. Let's see. That looks like it's in mode 2 to me, which is probably wrong. Let's just see what mode. I have to go back and check. So, no, it is this way around. It's kind of bizarre. You can see that if you like kind of like mode 1, this is, you might think this is the more significant bit, but it's not being interpreted as the more significant bit. Don't ask me why, ask Intel, but the labeling is correct according to Intel. So we're doing this mode, which is 8-bit UART, using timer 1 to generate the pulses. So that means SM0 has to be low, SM1 has to be high. So if we go down here, SM0 low, SM1 high. So that's basically putting the serial interface into mode 1, 8-bit UART mode, driven by timer 1. This bit just leave low, it's only for multiprocessor communication, we're not fiddling with that, fine. This is saying switch on the receiver, because otherwise you'll ignore anything coming into your microcontroller. So that's the receiver enable. These bits are left clear because we're going to be using 8 bits of information, not 9, so they won't matter, so we're leaving those low. And then these are going to be set automatically when things happen. We don't have to configure those. So you would write to the SCON register this number, which would be 50 hexadecimal. Okay. That's configured the serial interface saying, I want the serial interface to be in mode 1, driven by timer 1. We've got to configure timer 1, so that's what this is doing, and these 2 things together. So this one here, now remember, those 4 bits are for timer 0. We're not interested in those. We're only interested in timer 1, which is these 4 bits, and we're putting it in timer mode, because this is low. We're not using the gate. And this combination of values is actually the combination of values you need to put it in mode 2, which is 8-bit auto reload. If we look in this one, the only thing I've done here is I've switched on the timer run 1. Otherwise the timer wouldn't be timing it wouldn't count. So that switches the counter, and all the rest of it I'm not interested in. Now automatically, when it's appropriate, the overflow flag will be set here. Now when the timer overflows, and it's being used to drive the serial interface, you don't have to worry about clearing this flag. When we're using this timer to drive the serial interface, effectively looking after that is done for us. The final thing I've got to do is because I'm asking for auto reload mode, I need to know what's the auto reload value to put into my counter, the low part of the timer. And that's this number here. Now where did this number come from? That came from this calculation that we did down here, which is basically saying that's the rate at which we had here, which is 9,600 times 32, 307 kilohertz, that's this thing here. Then we worked out, in fact, 922 or 0.922 megahertz or 922 kilohertz is the rate at which this timer will be counting if we had an 11.0592 megahertz crystal. Why is that? Because the crystal's clock is divided by 12, effectively to perform each machine operation, or I'll rephrase that. It takes 12 clock pulses in order to complete one machine operation, such as adding one to the counter. So if that's the crystal speed, a twelfth of that is the time, is how fast this does its job. And a twelfth of that happens to be 922 kilohertz. So if you like, the timer is counting at a frequency of 922 kilohertz. But we want the pulses coming out of it to be at a frequency of 307 kilohertz, so we need the timer to go through a certain number of steps. How many steps? Divide that by that, and in this case it's precisely 3. And that's the reload value that we need. 3 less than 0, which we worked out down here to be FD. And so this number that's going into the upper part of the timer is FD. So what's going to happen is each time the timer overflows, it generates a pulse, which feeds into this divide by 32. And automatically the low part of the timer will have this number overwritten in it again. And it will do that forever. Okay? So that's all the configuration that we would need to completely configure the serial interface. So it's tedious, it's not the most user-friendly of things, but it's only 4 registers that we need to set up, and once it's done, that's it. So in fact, here's an example of a little bit of code that simply does what we had on the previous slide. This is all you would need to write to configure the serial interface using this crystal for this baud rate. So this is loading 20 hex into the TMOD register. That's the 8-bit auto reload configuration. Loading 40 into TCON is switching on timer 1, so it's starting to run. That's the reload value going into the upper part of the timer, so that when it does overflow, that will automatically be copied into TLOW 1. Okay? There's an 8-bit auto reload. The timer, which is 16 bits, is chopped into 2. The low part and the upper part. The timer is only using the low part, but when it overflows, what's in the upper bit gets copied into that again, automatically. And then the last thing we're doing is configuring the serial interface to basically say, I want the serial interface in mode 1, driven by the timer. And that's it. At that point in time, now this is being done as a call to a subroutine, which is why there's a ret instruction in this particular case. Once that's done, you've configured the serial interface, done. So it wasn't too painful. This is reminding us now about how TI and RI work. The transmit and the receive interrupts, which are actually 2 flags within the SCON register. Okay? So it's telling us that basically if you send anything to SBUF, once it gets transmitted, the final bit of information has been transmitted. In fact, it's actually after the stop bit has been transmitted. Then the TI flag will automatically go high to tell you, okay, it's done. It's your job to deal with that. Similarly, if any data was to arrive in SBUF, if it all comes in and it's correctly formatted, then upon reception of the stop bit, then the receive interrupt flag will go high. Whether or not it actually generates interrupts depends on whether you've enabled the serial interface interrupts. Here's an example of a little bit of code now for sending something and receiving something. And we're not using interrupts in this case. So this is just to send a character, an ASCII character. So all you need to do to send something is, first of all, before we send it, we're clearing the transmit interrupt. Just making sure it's clear beforehand. And then we're copying into SBUF the contents of the accumulator. Just simply copying anything into SBUF will automatically start the transmission. And the transmission will happen at the rate that we've decreed. You can then get on and do other things. Now in this particular case, we want to know when it's finished. And we're not using interrupts, so what we're doing here is entering this loop where we just keep on testing the transmit interrupt flag. By the way, you might say, well, why did I use scon.1 here when I'm using ti here? They are identical. I never wrote this bit of code, I don't know who did, but you could have written clear sti here, and you could have written scon.1 here. It's the same bit in the same register, just two names for the same thing. And I have no idea why we've written it first one way and then secondly the other way. So what we do is we write to SBUF the data. Now, in 8051 terms, it's going to take, if it's going out at 9,600 bits per second, that's actually quite slow. Remember, this microprocessor typically does about 1 million instructions a second, so it's going to have to wait for a little while to make sure all the data's been sent. So it keeps on testing that flag, which it cleared up here. When this flag goes high again, it knows that the data has been transmitted. And then we just leave this little subroutine, knowing that the data's been sent. Okay? In order to check if something's come in, there's a little bit of code here where we're just testing the receive interrupt flag. I wouldn't recommend this as a particularly good piece of code, by the way, because this piece of code, when you jump into this subroutine, basically you're going to stay here forever checking this flag until something does actually arrive. And if it doesn't arrive, you'll be here a very, very long time. So not necessarily the best code. But what we're doing is we're simply just checking the receive interrupt flag. When it goes high, we know that something's arrived, and so we jump to, well, until it goes high, we keep on testing it, which is why we're in this little loop here. When it goes high, we break out of this because the bit is set then, come down here, and we simply copy from SBUF into the accumulator whatever we found in SBUF. Now, the last couple of bits here, a bit of an unfortunate terminology, the reason why we're doing this instruction is whoever wrote this, the assumption is they're dealing with ASCII characters. And although we're receiving 8 bits of information, ASCII only has, the lowest 7 bits actually have meaningful values in classic traditional ASCII. So the most significant bit we're not interested in. So to make sure it doesn't influence our decisions, we're masking it to basically make sure it's a 0. And then the final thing we're doing is clearing the receive interrupt flag. Just to say, okay, just make sure I've cleared it now, to make sure I know that we've finished reading it, and so on. And then later on, we could come back in here, knowing that the flag's clear. If this has gone high again, we know that some more data must have arrived. And that's it. Like I say, in this particular case, although we're using transmit interrupt and receive interrupt, we're using them as polling flags. We're not using interrupts. And it's our job to clear these flags. And if something comes in and you don't read it quick enough, you'll overwrite what was there before, you'll lose it forever. A more elegant solution to this, a better way of doing it, would be that you basically enable the serial interface interrupts, and then you would only jump into these routines when you know something's happened. And that would automatically happen if this goes high or this goes high. Yeah?
What was JNB?
Which one?
What it says JNB.
J and B, jump if no bit's set. So it's a conditional jump, and it's basically saying if the bit I'm testing is not set, do this jump, which means we're going to keep on going around here. And the bit we're testing is the receive interrupt flag. So jump if no bit is set. In other words, if this is not set, i.e. it's low, jump to this place, which means we're going to be doing this all the time. However, when this flag goes high because something arrived, you won't perform this jump because the bit is set, in which case you just carry on down here. Yeah?
How does the hash 7FH mask off the ASCII's 8 bits?
All it means is what another bit of code is probably going to do is going to do some kind of lookup in a table or something like that. And because there are only meaningful values from, I don't know, D0 through to D6, the D7 bit, if you like, the most significant bit, has no meaning. What we don't want, sometimes it may be that the sender made this high and sometimes low. We don't care about that because for us it's not meaningful. And to be absolutely sure it's not going to influence, because if you're doing a comparison, you might be doing a comparison. Let's say if you want to look for a particular ASCII character. Well, let's say the ASCII character for space is the code 32 decimal, I think. But that's a 7-bit representation. But in your comparison, you might be comparing 8 bits with 8 bits somewhere else. What you don't want is the most significant bit, depending on its value, to, if this is matching that, depending on this, you may, if this is high or low, you might get a match when you do the comparison, or you may not. I'm making it sound difficult. Let me think how I can express this.
Oh.
You could, well, 32, what's that? 0, that's the 1s, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s, the 1 to 8s. So let's say that you're testing it to see, have we got a space that's arrived? Now, in fact, what comes in, it's only those bits that are actually meaningful. But what happens if we're doing a test on the whole byte? Okay. Now the whole byte would have the number, if we chop this, that would be 20 hex. If this transmitter happened to have sent a 1 here instead, we'll end up with the number 50 hex. Now, in terms of the bits that matter to us, they're actually the same, because we only care about the lower 7 bits. But if we were to do a test on the whole byte, we basically say, has the byte come in equal to 20 hex? In the second case, the answer is no. But actually, in terms of the bits that matter to us, it is actually the correct character, the character we're looking for. So to make sure that this most significant bit has no impact on our things, we want to force it to a certain value. So we're masking it with this thing here, so that no matter what this 7th bit is, we're ANDing it with 7F hex, which will mean that the result of that will always make this 0, this bit, no matter what. So it's impossible to ever, even if something 50 came in, it would be converted to 20. I'll leave it like that for now. If you want me to go through it again, just ask me after the lecture. But it's just, it's simply because we know that in the data that comes in, only 7 of the 8 bits actually matter to us. So for the bit that doesn't matter, rather than not being sure what its value is, we're forcing it to a known value. Okay. So now we're moving on to the next topic from last week that we haven't yet done.
Excuse me.
Yeah? Oh, sorry.
If you're doing interrupts,
Yeah?
so when you jump, do you have to first check which one is set
In the-
high and then again jump?
In the case of the serial interface, if you're using interrupts,
Yeah.
no matter whether it's the TI flag or the RI flag that caused the interrupt, you won't know. You'll jump to wherever it tells you in the vector table to jump to, where your code's sitting. It's your job to do 2 things. It's your job to work out, is it the TI or the RI flag that's caused this interrupt? It's your job to clear the flag, and it's your job to take whatever action is necessary. Now, it could be, yeah?
Does interrupts clear the flag after that? Or
Not, it does normally,
Yeah.
but in the case of the serial interface, it's an exception, and the flag does not automatically get cleared when the interrupt is called. It's your, I think in the case of the serial interface, you have to manually clear the flag.
So do you lose any machine cycles in that? How many machine cycles do you use?
Say that again?
How many machine cycles do you use or lose?
For doing what?
To
Clearing the flag.
It doesn't matter how